So first and foremost here, goal today is to get to our homework, which 5, 6 problems, something like that. They're based on just equations, something simple. You have to tell me the critical points, inflection points, if it's a max or min over your little boundary that you're in, and then tell me the concavity. So if it's concave up or concave down, that type of thing. So just make sure of that you're paying attention to that for the problems, so you'll be able to take the first derivative of them. I picked simple equations. There's only one that you actually have to spend a little time on and think about, like, how do I actually find the critical points on this particular problem? So I'm going to need to spend a lot of time on No. It's if you just think about what you need to find, there's a shortcut to it. Tomorrow. So, okay, but these are going to be due on Wednesday. Now, I'm going to bring this up. This is not what your homework is. This is the Google question of the day that we did Friday. This isn't the exact one. This will help you with the concept if you know if it's a max or min. Okay, so if you do the first derivative, okay? Wednesday. So if you do the first derivative here, and so what I'm looking at is I'm looking at this row right here, if you're looking at those. Okay, the first one, the derivative is less than 0. Down, and then it goes above 0. So it goes up. Then it keeps continuing to go up, but it actually hit 0 in between there. So it kind of probably flattened and then kept going up. So the idea here is that this is probably what my graph looks like. I can get a sense for the graph before I even move to the next line.
So this is not right.
Okay? Now, why did I bring this up? This actually tells me, by just looking at these objects can tell me if it's a max or a min or what it is.
Okay, but the problem is mine looked like a W.
No, that's fine. This wasn't the one from Friday.
So it's
I said this is a different one than the one from Friday. It's like what we had to do for the question. Okay?
I just didn't listen to the
question. What? Yeah, it's a minimum. Now, here's the reason why. Hey, anytime your first derivative goes from negative to positive, you have a minimum. Okay? So this causes a minimum on the graph. So how we do it when you just have a normal equation? What?
Or an absolute?
Potentially an absolute, depending on how big your range is, like the domain. I mean. So that would be an absolute just in between there. The only thing I'd have to check to see if the outer points here actually dip lower.
And then if they did, then it'd be Alabama.
Relative.
Oh, okay. Sure. That was above my head for about 5, 6 seconds there. All right. I thought I missed something there. All right. Anyway, now when we go to the next part, the second derivative should just confirm that your drawing was correct. So the idea is that on this one, we are concave up. This is concave up because we're above 0, up till about x3. x3 should be about halfway between x1 and x2. This is x2, this is x1. The x's are where you hit your point where the derivatives flatten out. So I'm halfway between there. So the idea is that this is concave up, which it is. Then it goes concave down.
Back down, boy.
Then it goes back up, and that makes sense for what can hold water and what dumps out water and what holds. So it just confirmed what I'm looking at. These are the things you're going to have to tell me for your equations today. So as you go through it, maybe outside the boundary you don't have any concavity like down or anything. Maybe it's just concave up over the life of your function. Because I'm going to limit every problem between this number and this number. I think there's only maybe one question that you have where you have to go as far as you can. Where it goes from like left to right to negative and positive infinity. So just make sure of that. Okay, all right. But that's kind of what we're looking at. Now again, I'm not giving you these tables. I'm giving you equations, and you have to follow this type of math and this type of reasoning. Okay? That's why I gave you these last week, just so you could like look at this and know instantly what you're looking at. I make these little tables on my little like paper for each problem when I do it. I make a little like first derivative table. I make a little second derivative table like this. And that helps me figure out, is it concave up? Is it down? Is it a minimum or a maximum? Is it just flattening out? I make these things for each problem. Okay, so let me give an example of what I'm talking about, how to make one of these. Okay, let's say this is my problem. This is my only example. This is my last slide. I know it says like 15 down there. Those are from last week. I just didn't delete these slides. This is my last slide today. I'm gonna set up my problem, this thing into that little table and do the first derivative, second derivative. Okay. So, first derivative to figure out my x1, x2, x3, whatever I have. Okay, so first derivative test. Okay. First derivative is 3x squared minus 20x minus 9, right? So if I can factor this thing apart, potentially I could see, you know, where my numbers come out. Maybe this thing isn't factorable. If it's non-factorable, you just do the quadratic formula. It tells you where your x's are, because this is a quadratic. Everything you have should be either factorable, or you can plug it in the quadratic formula. I want to see if this is factorable. I don't know if it is or not. So let's see if I can factor this thing apart. So it's going to be plus minus. We got to subtract to get 20. So let's see. Geez, what can we do?
3 and 1, isn't it?
Yeah, well, I got to go 3 and 1, but I don't know if it's 1 and 3 or 3 and 1. And then breaking up 9. 1 and 9 or 3 and 3. So it looks like that will not be factorable because I won't be able to make 20 in the middle. So I'm just going to go right to the quadratic formula and get my x1 and x2. Okay, so the quadratic, if you don't remember,
The number in front of the x, it's automatically not factorable, basically.
What? No, it's no.
I suck at it.
No, I mean, you just got to check. So quadratic formula, opposite of b plus or minus square root b squared minus 4 times a. A is a 3. C is a negative 9. So it ends up being an actual number, so I can actually take, and then this is 2 times a. So it actually ends up being a number. So this is 20 plus or minus, this is 400 plus, what is that? 12 times 9, is that 98? What is that? 12 times 9 is 108. All over 6. So that's pretty much why it wasn't factorable. This turned out to be a square root of a 508, and that is not really factorable, so that's why I couldn't factor it apart. Now, the potential numbers there are those two numbers. If you want to type it in your calculator, 20 plus the square root of 508, square root of 508, that number, and then divide by 6. One of the numbers is 7.1, and the other number, if I take 20 minus the square root of 508, divide that by 6, I get negative 0.4. Oh.
Your palm rule.
Yeah, I wish I could turn that palm detection off. There we go. Negative 0.4. All right, so those are my two numbers. So now those would be the potentials for my critical points. Now one of these I have to throw out. Which one?
What do you mean?
I have to throw one of my critical points out. Yes, I have to throw out 7.1 because it doesn't fit
In your line of 5s.
Yeah, I have to be between 5 and negative 5.
Can I go to the bathroom?
Yes, now you can.
Okay.
Okay, so that's doing the first derivative. Now, the problems you're going to have, they're either going to be factorable or they're going to come down to this where you can actually take the actual square root of it. Or I should say the quadratic formula of it. Okay. All right. Okay, so in this particular case, now what I would do next is set up my little chart to figure out if that's a max or a min. So, all right, so to figure out if that's a max or min, here's my little table. Okay, so the outsides were negative 5 and positive 5.
Yep.
And in the inside, it was like negative 0.4. That's where that max or min happened. That was my x numbers. So what I'm going to do is I'm going to check what the first derivative is doing around those numbers. Okay, that'll tell me if it's a max or a min or what number is this negative 0.4. Maybe it was a hilltop. So what I'm going to do is I'm going to use that first derivative, which what was the first derivative formula I had written down?
You want the first derivative?
The first derivative. Say it again.
Minus 9.
3x squared minus 20x.
Minus 9.
Minus 9? Okay. All right, so just plugging in numbers. I'm going to plug in numbers over here and over here, and I'm going to plug in the easiest numbers I can. And all I need to know is it positive or negative around there, because that tells me if the first derivative is positive or negative around these numbers. I'm not going to go outside the negative 5 and 5. I don't really care.
Negative 4.
So yeah, sure, we plug in negative 4. So I'm going to take my equation. I'll show you my little calculator here in a minute. 3 parentheses, I'm going to type in negative 4 squared minus 20 times negative 4 minus 9. So I'll show you my little calculator here.
Positive.
I forgot to get out of the power when I typed all that. All right, minus 20 times negative 4, and I already heard it's positive. Okay, and it is actually positive. So when I typed in my numbers here, so I typed in all my numbers here, and so I am getting, so when I typed in a -4 into that first derivative, I got a positive 119. So it looks like on my particular problem, these were positives over here. So that means my first derivative is greater than 0.
Is this homework
So,
Thursday?
Wednesday. So, okay, now when I plug in the next number, so what I'll do next is plug in 0, because that's a number on the other side of -0.4. I got, or actually, let's plug in 1. 1 would be an easier number, so, because I don't like plugging in 0. 0 always causes issues with people.
So it doesn't matter what number.
No, I'm just picking numbers between -0.4 and 5.
Still -9.
Yeah. So you get -9. It's gonna be negative. So, so if you plugged in a 1 or you plugged in any other number you want between there. So I'm plugging these in the first derivative. I got a negative number. I got a -26. If you plugged in 0, you got -9. So it looks like my first derivative is less than 0. So what was happening? It was going up and then it was coming back down. So that spot was a maximum. So that's really what I want to know. I want to know, was it a max or a min? Like, can you identify what the critical points were by just using that first derivative little test? Okay, so when you actually write out your answers in your Google form, you'll say, okay, it was -0.4. Again, I rounded that number.
Wait, go back to your drawing.
Yep. I didn't have a drawing of this one.
Oh.
So, did you want the original equation or did you want?
No.
Okay, well, between this was a maximum. And so what I would do on my Google form, I would say, okay, -0.4 was a critical point between -5 and 5. We threw out the 7.1. And this was a maximum because of the slope, right? So you'd say it was a maximum. I don't care if you say relative or global. Just tell me it's a max or min. So we did that. Now the second part we have to do is the second derivative to figure out critical points. So we're going to have to do the second derivative now on this thing. Second derivative is 6x minus 20. So it looks like the second derivative will give me a critical point of, if I set this thing equal to 0, I don't even need to factor anything, I can just solve. So add the 20 across, divide by 6. So it looks like my other critical point on this problem is a decimal, 20 divided by 6, what is that? 3.3 repeating. So I actually have a critical point here. Or inflection point. So the inflection points here was 3.3 repeating. So this was if I get rid of that was a critical point, or inflection, I keep saying critical. It was an inflection point. Come on, let me draw it. All right, so that's an inflection point. And so what I'm going to do is just figure out, to this side of it and this side of it, like, is it concave up or down? That's really all I need to know. Obviously, these hash marks continue all the way down. So you probably should check what's happening between all of these. So there's actually like 3 spots I need to be checking to see what concavity is doing at this moment.
Wait, 3.
Because
Did you ignore the first one?
it was the 0.5 to the -0.4, so there's like one gap there. There's another gap between -0.4 and 3.3, and another gap between 3.3 and 5. So there's like 3 gaps I need to check for concavity. Because I continue these hash marks straight down, so I'm checking the gaps from here to here, here to here, and here to here. This is what I'm checking for inflection and concavity. Does that make sense? Okay. I'm betting on there's probably only a switch right at that 3.3. There's probably a switch there. The other ones probably didn't switch, but I don't know. We'll see here in a second. So second derivative, so what I'm going to do is take my second derivative and plug in numbers. So I'm going to plug a number between -5 and -0.4. So let's say I plug in like a -4 there. So I'm going to take that equation. 6 times a -4 minus 20. That turns out to be negative. So my second derivative here ended up being less than 0. These are all negatives. So it's concave down in that range. So This is concave down here. And I would say, you know, between this number and this number, it's concave down. The next number, I'm going to try to number between 0.4 and 3.3, so I'll plug in like the number 1. And again, I'm using the second derivative to tell me this. This turned out to be negative as well, like I kind of warned you of. So second derivative ended up being 0 again. So this was negative, and I plugged in a 1. So these are all negatives. So it's still concave down here. And plug in a number between 3.3 and 5, I'll plug in 4, and that turns out to be positive. These were positives in here, so this was concave up over here. So probably what happened, it was probably something where, you know, if I'm looking at this kind of logically, it's probably doing something like this. It did a hilltop, and then it probably flattened right after this point. So it was concave down, you know, it was concave down all the way over here, but then suddenly, like on this side, it was going concave up. That's probably what was happening. It was probably bowing. And so, and it could have been right after the 3.3, it started bowing upwards. So, yeah, so, and that makes sense because we found, what was it, 7.1 was my other number.
Yeah.
So it probably had another critical point coming up down the road where it probably was like a minimum going back up. And so that's why it's changing directions to go concave up. Now, what you'd actually tell me in the Google form, you tell me, okay, it's got a max at negative 0.4. It's got concave down from, you know, negative 5 up to 3.3, and it's concave up from 3.3 to 5. Like, you just tell me, like, in detail, like, the words. That's all you're doing. Does that make sense, what we're attempting? I gave you all normal equations. There's only one that you're going to have to spend a little bit of time on. We're going to probably talk about it tomorrow. So if you get that problem right off the bat, just ignore it, come back to it. We might talk about it tomorrow. And trust me, you'll know which one I'm talking about when you see it. Okay? I have it picked out. In fact, it's already on my next slide. I'm just not going to show you. So
Next slide.
we'll look at it probably tomorrow. So, yes. All right. That's it for today. Yes, you may.
Oh my God.
I'm going to leave this up here.